Good morning, everyone. So I'll be presenting the DTOceanPlus Environmental and Social Acceptance module, which is a tool to optimize arrays with a reduced environmental impact and increased social acceptance of ocean energy. This work has been mainly conducted by Emma Aranius, who is engineer at France Énergie Marine, in collaboration with Rui Duarte, Johan Carvela, Nicolas Germain, Rotsui Zorna, Morgan Lejar, Nel Luxey, Nicolas Michelet, and myself, Georges Safi. The DTOceanPlus set of tools comprise the Structure Innovation tool, which is a concept creation using a structured approach to address ocean energy engineering complexity. The StageGate tool, which provides the framework within which the deployment and assessment tools can be applied. And then we have the deployment tools and the assessment tools. In the deployment tools, we have the site characterization tool, but also energy capture, energy transformation, energy delivery tools, station keeping, logistic, and marine operation planning tools. And in the assessment tools, we will assess the system performance and energy yield, its system reliability, availability, the system lifetime costs, and also the system environmental and social acceptance, which is the module that I will be presenting. The ESA tool will provide the user with 4 different assessments. First of all, there's the first assessment about the presence of endangered species in the area. And the endangered species list has been classified as such by the International Union of Conservation of the Nature and are listed in different conventions and European directives. So we consider the different regional conventions such as the OSPAR Convention, the Barcelona Convention, the HELCOM Convention, international conventions such as the Washington Convention, the Bonn Convention, and also the directive such as the BIRDS, the Habitat, or the Marine Strategy Framework Directive lists of endangered species. And based on all this information that are included in the tool, the first assessment will be to identify the presence or not of this endangered species. The second assessment will be about the environmental impacts characterizing pressure receptor interactions. And in the second assessment, we will have 11 different metrics such as collision risk or underwater noise that will be considered in order to produce an environmental impact assessment. The third assessment will be about estimating the carbon footprint of the project. This assessment is commonly used in different industrial applications. And the final assessment will be about improving social acceptance of the project. And here we will consider different metrics such as the number of jobs created or the cost of the energy that will be produced. So now I'll be developing a little bit more each of these 4 main assessments. First of all, the presence of endangered species in the area. The user is requested to inform about the coordinates of the array, and these coordinates can be either directly given by the user if he's using the ESA model as in a standalone mode, or this information can also come from another tool, which is the site characterization tool. And once we have these coordinates, in the module we have included maps of probability of presence of endangered species. And from these maps, we will identify if the species have a probability of presence in the area or not. And the output of this first assessment will be to list the species that are present. And for each species, we will have information about it. And we will also have specific recommendation, either protocols to how to service the species, or recommendation about how to mitigate pressures that can affect this given species. The second assessment will be the environmental impact assessment, and this assessment is based on 11 metrics, which are energy modification, footprint, collision risk, chemical pollution, turbidity, underwater noise, electromagnetic field, and temperature modification. And we also added the 3 additional metrics that are rather considered as positive metrics, which are the reserve effect, the reef effect, and the resting place for the species. So, in order to explain how we calculate the score for each of these metrics, I will give an example about the energy modification, which is the resource reduction. So the user is asked to inform about the percentage of resource reduction. So either the user can give directly this information in a standalone mode, or this information can also be given from another tool. Here it's the energy capture tool that can give the information about the resource reduction. And from this information, 3 steps will be applied. The first one is to calculate a pressure score affected to this resource reduction. This pressure score is also adjusted, PSA, is adjusted with information about the receptor being either a species or, here in this case, type of soil that is in the area. So the first pressure score, as you can see in the table on the left, is directly related to the percentage of resource reduction. If this resource reduction is less than 10%, we consider that the pressure is the lowest. And if it's more of 30% of resource reduction, we consider that the pressure is at the highest score. From this first score, PS, we will multiply it with a weighing score related to the receptor. In this case, it's the type of soil. So if the type of soil is a rocky soil, we will have the lowest pressure. And if it's a sandy soil, we will have the highest pressure, because sandy soil are considered to be more affected by resource modification. And this weighing score is between 0 and 1, and by multiplying the pressure score by the weighing score, we will have a pressure score that is adjusted. So this is the first step, and the second step will be to consider the sensitivity of a specific habitat in this case. So if we have, for instance, a particular habitat such as zooxanthella beds or marl beds, we will apply the highest receptor score. And according to the type of habitat that we have different scores that will be applied, considering the sensitivity of the habitat. So the second step considers the sensitivity of the habitat, and the last step will be to apply a linear mapping, a negative linear mapping in this case, in order to have the final score that is between 0 and -100. And in the case of positive impact, when we consider the reserve or reef effect, for instance, we'll apply a positive linear mapping in that case. And in other metrics, we have an intermediate step between the step 2 and the final score, which is to consider the seasonality. For some species, such as marine mammals, for instance, we know that they can be present only in certain seasonal period. So we have a third step that is similar to the step 2, but that considers also the seasonality. So we can have the information also detailed according to the seasons of the year. Once we have calculated all the metrics, all the 11 metrics, the final output will be given in a global score, which you can see under the metrics table. So we have a global score, which is divided into 2. We have the negative score, like here, for instance, -42, and under the score we have the standard deviation. So -42 is the mean value of all the scores obtained for the different metrics, negative metrics that were calculated. And we have also information that is separated regarding the positive score, which is related to the reef, reserve effects, and the resting place. And again, we have the standard deviation about this final score. So we can have this global information, but we can have also a detailed information about the metrics. Here, for instance, for electrical components impacts, we can see the details of the different metrics, of the scores of the different metrics that can be given also by as an output of the ESA model. And finally, with these scores, we will have also recommendations that are associated. So here, for an example, for the energy modification, if we have an impact that is higher than 20%, the recommendation can be to consider reducing energy extraction to less than 20%, and the ideal level is set to be less than 10% in order to have the lowest possible pressure. So we have recommendations also that are given with the final scores. The third assessment is about carbon footprint of the project. And here we have followed, in order to develop this methodology, we have followed international or recognized standards, which are the ISO 14040 and ISO 14044 standards. And in this methodology, the inputs that are requested from the user will be to give information about, for instance, what are the materials that are used, their quantity, what is the fuel that is consumed for the transportation, etc. So we will have a list of inputs that are requested, and the outputs will be two main midpoint indicators or metrics, which are the global warming potential, GWP, which is calculated in terms of carbon dioxide emissions per megawatt produced, and the cumulative energy demand, CED, which is calculated in terms of total consumption of primary energy per energy produced. And the final outputs of this assessment will be a global value for the GWP or the CED, and for each one of them we can also have more detailed information according to the different phases of the project, from the fabrication up to the dismantling and treatment of the materials. So we will have these two levels of information and scores for this assessment. And the final assessment is about the improvement of social acceptance of the project. And for this assessment, we have two metrics that have been included in the ESA model at this stage, which are the cost of the energy and the number of jobs that are created by this project, which are of social acceptance relevance. Finally, the general outputs are different according to the level of complexity of a given project. So here in the table, you can see that we have three different columns that give information about the availability of the metrics according to the complexity level of the project. So we have the early complexity level, the mid complexity level, and the late complexity level. The early complexity level refers to early stages of conception of an ocean energy project, and in this case we consider that we are capable of giving at least the information about the presence of endangered species. As soon as we have a site that is identified, we can give this first assessment. And regarding the other metrics, it's most probably not enough advanced to have the requested inputs in order to run them. But these inputs will be available the more we go towards the late complexity level. The mid complexity level being referring to stages where the ocean energy project is at the design optimization and feasibility stage, and late complexity level refers to commercial area demonstration scale, where we have the project that is mature enough at this stage. And the user will be able to run the ESA model either by a standalone mode or by in interaction with the other tools. And the final score will be the impact scores, different impact scores according to different assessments. And also, what is very important in the ESA model is the recommendations, where we give recommendations either for either protocols to survey the potential impacted species, and mitigation measures to how to reduce the impacts according to the different potential pressures that can be induced by the array project. Thank you for your attention. I'm ready for any question now if you need. Thank you.